again that the intensions of a function are what we call its limit. Let me say that again. The intension of a function is what we call its limit. Now, make that your first recording. Record what it means to be a limit. What is a limit? As you write down what you see up here, I want you to realize that it's like the intention of the function. Now we have some other pieces to this. This thing about x approaching c, that little arrow means x approaches c. And I'll show you how that works into this idea of an intended height. An intended height. And so the intended height, so to speak, the intention of a function, well, that ends up being the limit. Now we're going to analyze this a couple different ways today, so don't try to figure it all out with just one definition, but we're going to analyze this a couple different ways. One of the ways is going to be with a graph, and that's the way that we'll start. It's always a little nice because it's obviously visual, and you'll see what we mean by the intended height of this function. So this function here, let me make that just a little bit better. Sorry, I want this to be good here the first time through. We'll do it like that. All right, so we'll put a couple important locations on here. Could be drawn to scale a little better, but we have the idea. We'll call this f of x so that we can talk about some limits. Now, one thing with limits, as with many things in math, is that it has a notation. And I'm just going to jump right in and show you the notation because it's not hard to start to understand. First off, we just abbreviate the word limit. It'll always be abbreviated LIM. Second of all, the x value that you are approaching will always be written under that abbreviation. And so when you sort of package it all up, you would say the limit as x approaches 2 of f of x. Again, you would read that as the limit as x approaches 2 of f of x. Now, let's approach 2, but as we approach x equals 2, notice that I'm going to approach it on the function. So as I approach x equals 2, my finger, might be moving this way. Okay, so I'm kind of moving this way, or I could move this way. And ultimately, what I want you to realize is that either way that I move, I'm approaching x equals 2, and I'm getting to an intended height. Now, that intended height is not supposed to be a trick. It's the height of 1. It's the height of 1. In fact, not only do I intend to get to the height of 1, I do get to the height of 1. So the intention of that function is to approach y equals 1. Okay, make sure you just notice real simple here that the answer to this is a y value. The answer is a y value. I also want you to realize that there are many different limits. In fact, there's arguably an infinite amount of limits, but there's other limits on this function. I don't want you to think that the only limit would be the one as x approaches 2. We can have the limit as x approaches 0. Okay, now it's just kind of something to watch. It's not really that amazing, but it's important to watch as I approach x equals 0. And so as I approach x equals 0, I could approach on this side, or I could approach on this side. Okay, so this space up here is x approaching 0. Now, there's an intended height. There's a y value. It's not supposed to be a trick question. It's the number 3. In fact, the function reaches the number 3. And so we call that its limit. Okay, now again, don't try to figure everything out through one example. Okay, but for this particular problem, you should be kind of saying, well, Ms. Naylor, it looks like these two limits are actually the actual values. Yeah, they are. That is definitely true. So take that thought and let's look at another function. Let's look at g of x. We're going to get this drawn good. Get a couple numbers on here on the x and y axis. Okay, so just to make sure you're seeing what I'm trying to draw, it looks like we have a straight line. It's got a hole in it. Okay, so there's a hole in the graph, and then there seems to be this disjointed point. There's this disjointed point kind of floating up above. How about the limit? Oh, let's call this g of x. My fault. Let's call this function g of x. How about the limit as x approaches 1 of g of x? Okay, now I find that kids catch on to this, but I just want to make sure that you're kind of looking at the graph the right way. When we say x equals 1, okay, then we would be either approaching x equals 1 like this or like this. So I'm approaching x equals 1, but I'm doing that on the function. So your eyes, your fingers would be getting to this spot right here. And sort of the big question for this problem is, what is the intended height at that spot? What is the intended height at that spot? Okay, well, the answer would have to be 2. Okay, the answer would have to be 2 because if you think about it, on each side, I'm getting closer and closer to a y value of 2. Now, if you're saying, yeah, but, well, what's the but? Do I actually get to that y value? Do I get to it? I do not. There's a hole in the graph. But here's the thing. It doesn't matter. A limit is just an intended value. Okay, so that's kind of your next sort of key idea. Although it's the same idea, you have to realize that it's okay that the value is not there. It's just an intended value. Now, if you're saying, what's this point up here? Well, it's kind of there to be a little bit of a teaser so that we realize that the value f of 1, so the value f of 1, now make sure you get my notation. I know it's notation from years gone by. I know you've seen it before, but f of 1 is straight up referring to the actual value. I mean, we can put the word actual in front of it if we need to. But f of 1 is referring to the actual y value. Now, the actual y value would be this point, which is just kind of hanging out up here at 4. The limit does not equal the value. The limit of 2 does not equal the value of 4. If you're saying, am I supposed to do something with that? Yeah, I just want you to listen to it, okay? Because it's going to come back up, and I basically just want you to realize it's okay. Now, over here, the limits did equal the value because I did get to y equals 1. The limit was equal to 1, but I did get to that. That can happen. Or over here, my limit, my intended height is different than my actual height. And that can happen. Okay, that's okay. Okay, a limit, it's just an intended value. Let's do this one before lunch. Let's do this before lunch. Okay, little different presentation, right? Now I'm asking you to find the limit of a function, of an equation. Okay, so, geez, what are we going to do? Where are we going to go to be able to find that intended height? Okay, well, as I want you to realize from this problem, we still can go to the graph. We can still go to the graph. Okay, because graphs show y values. Graphs show y values. Now, I encourage you as always to play along. There's going to be multiple times this year where we appeal to a graph. I just find if you're actually pushing the buttons and you're looking, you get one step closer to that understanding on your own. Okay, so the argument here was, let's graph this so that we can see the y values. Sometimes when you're graphing anything with a trig function, there's a little bit of uncertainty. Am I doing it right? I get it. Okay, trig functions are kind of new. Just some thoughts. Make sure you're in radians. That's always the case downstairs in calculus. If you do see a trig function, hitting zoom trig, I would say, is always a good start. When I say start, it might mean that you need to change it, but let's see what happens when we hit zoom trig. So a good sign, we get a graph. Okay, now, yeah, that'll work. That'll work. So let's sketch it. A lot of times you're doing an assignment and you're doing something with a graph, you're going to want to sketch it. Okay, now are you ready to go to x equals 0? Okay, so you can hit your trace button or you can watch. You might do a little bit of both, but we're going to try to get close. We're going to approach x equals 0. Now, as I approach x equals 0, I see some y values, like I happen to be at 0.86 as a y value. I get a little closer, I get to 0.9. Okay, 0.95, 0.97, 0.98, 0.99, blank. Now, it looked like I was on sort of a roll there. 0.8, 0.9, 0.99, and then it went blank. How about on the other side? Okay, a little more quickly, you can see that you're at 0.9, 0.95, 0.98, 0.99, and then it vanishes. Okay, now what's happening here is that there is no y value when I go to x equals 0 because there's another one of these holes in the graph. There's a hole in the graph. Okay, I just kind of want you to realize that the calculator didn't really show that until I investigated a little bit. Okay, so I investigate and I see that the y value disappears. That again is a sign that there's a hole at x equals 0. But now, as calculus students, kind of like the first day, but as calculus students, I actually want you to look at that and say, okay, hey, no big deal. There's a hole there, but I just need the intended height. Okay, so if we think about what was happening as I got closer on this side and on this side, we could say that that intended height should be and is 1. it should be, and it is 1. Now, if there's a little bit of kind of like a, how do I know for sure, Mr. Naylor? How do I know for sure? You should feel that way. And I will show you some other ways that we can basically find these limits. But right now, the argument is that you're just visually noticing what's happening with the numbers. Okay, and there's nothing wrong with that. But I will be giving you some methods where you'll feel like, okay, now I'm sure. In some cases where maybe you're unsure. When you get back from lunch, I'm going to show you a little video. So make sure you come back for that.